Today I'll skim over some recent work regarding deep generative models, especially for sounds and speech, but I'll say a few words about some of the new things we're doing with images. You're seeing here some of the generated sounds and images. These are pretty impressive. These models were trained to generate images from any of the 1,000 categories from ImageNet. And this is the book that I wrote with Ian Goodfellow and Aaron Kerville, which is very popular these days. And a good intro to deep learning if you're interested. So deep learning seems to be having a big impact in industry and bringing back the idea of AI, which had been kind of forgotten for a number of years. And what's interesting for this crowd is that deep learning is really a rebirth of ideas of the connectionists from the early 80s. So I made a list of some of the ideas from those years which you find in deep learning. Of course, the importance of learning is a powerful way to put knowledge into computers, and this is really important because what makes us and machines intelligent potentially is knowledge. The really central idea, I think, of connectionist approaches is that of distributed representations, potentially sparse. Of course, these representations are learned from data, they're not handcrafted, and they capture in a very critical way the meaning of the data or the state that is to be represented. Another important idea from these days that you find in multi-layer networks is that we're going to be learning functions, and these functions are going to be compositions of simpler operations. Of course, more recently we pushed that even more with the idea of deep learning, which just means we have many compositions, but the idea was already there. And another really important one, I think, especially if you think about how some of these ideas are, how people view learning in brains very often, is that these neural nets are jointly trained. In other words, all the components, all the layers are jointly trained with respect to a single objective that's meaningful from a learning point of view, from a theoretical point of view. And the way that learning works is by iteratively going through examples, each time slightly improving on minimizing that objective, and doing it in an efficient way. In artificial neural nets, we use backprop, but as I'll mention at the end, we're working on biologically plausible implementations of backprop. So it's not necessarily something that should be limited to artificial neural nets. Backprop exploits an efficient estimate of the gradient, something you don't necessarily find with other perturbation or reinforcement learning-based approaches to optimization. Another important idea is that the objective function we're optimizing is directly linked to either the task we're trying to have the agent perform, or capturing the data distribution. That's sort of the supervised versus unsupervised learning idea. But and finally, of course, what drove the connectionist ideas at the beginning is that the computations performed by the systems are, in the artificial neural nets at least, are inspired by neural computation. All right, so I guess you knew all of these things, but just want to remind you that it's still very much alive and an integral part of the successes that you've heard about recently. I think Antonio is actually sitting somewhere. And I want to mention, because I've been talking about semantics, and I'll say a few words about this later, that something we really strive for in building these neural nets is that they capture representations that have to do with what the data refers to, so semantics. And interestingly, if you analyze the top few hidden layers of these convolutional nets trained on images, you find that some units, a large fraction of the units, actually specialize to detecting categories which were not predefined in the supervised learning setting. And so these categories, those semantic categories like objects in rooms, wardrobes, mountains, beds, fireplaces, and so on, were automatically discovered by these learning systems in order to perform the task of interest. So this is recent work from Torralba's group, but there's a lot of other related work essentially telling the same story. And this question of learning semantic representations, I think, is very important, and it was my initial motivation for the work we did about a decade ago towards deep neural nets and deep learning and deep architectures. The idea in deep learning is that in addition to this notion of learning representations, that the representations are going to be at multiple levels, and higher levels are defined in terms of the lower levels, or vice versa, depending on which direction you want to go. And the higher you go in these representations, the more abstract the concepts being represented are. Furthermore, as you go really higher up, what you're doing is decomposing an explanation from the data into factors that we can think of as the explanatory factors and potentially the causal factors of what is being observed. So this is an intuition that guides a lot of the work, especially with deep generative models, which is what I want to tell you about next. Oh, and why I think this is important is because if you're able to do that, and we're not yet able to do that satisfactorily, then learning becomes very easy. Then you can learn from very few examples, a new task. Then you can get very powerful generalization. All right. Now, one more thing. One way to see why this is true is it's true for the same reason that good scientific theories work, right? Because there are good explanations, correct explanations to some degree for what we're seeing around us. All right, so the work in deep generative models, first of all, is driven by the idea that a lot of the data is unlabeled or doesn't have the kind of semantic labels we've had. So we'd like our neural nets to discover these underlying abstractions. And a really appealing notion is that these abstractions are the factors that generate the data. So we think of the way that the data was generated as we first generate those factors and then we generate the data given those factors. So there's been a lot of work in exploring different kinds of neural net architectures that can generate data of different kinds. And in recent years, there's been a lot of progress. And these are examples of things that were generated with various algorithms. One of the approaches that is popular, especially for sequential data, but as you'll see even for images, is the recurrent nets. And you've heard yesterday about LSTMs and recurrent nets in general, so I'm not going to spend too much time on the details, but the important thing to notice about recurrent nets is that they can represent a joint distribution, potentially capturing all of the dependencies between the variables in the sequence by decomposing the joint into a product of conditionals where you predict the next thing given everything before. And everything before is summarized in the state of the recurrent net, like these S variables at different time steps. So everything that came before is implicitly going to be summarized by the neural net. And it learns to do that summary in order to condition the generation of the next thing. And then we can use the log likelihood as an objective function where we're going to compute the log probability of the actual thing that happened given the predicted probability. And we're going to maximize those log probabilities. There's one thing that many researchers don't like about maximum likelihood, and it becomes clearer if you consider it with the old connectionist term of teacher forcing. So the way that a recurrent net or any other system is trained by maximum likelihood is we're going to, say, predict the probability of the next variable given other variables' values in the training data. So in the sequence, we're going to predict the next y given previous x's. And why is that a problem? Well, that is a problem because when we're going to be using the model to generate new sequences, or new images in this case, the configurations of the inputs that we're going to be seeing are not going to be the ones that necessarily come from the same distribution as what's being seen during training. They're going to be the ones generated by the model. So if I generate a sequence of sounds, and the sequence of sound that the machine generates doesn't look precisely like the things it's seen during training, then at generation time, it's like a different distribution that it sees as input, and it might do things slightly wrongly, and those errors can compound as we go further in generating more and more things. So that's something we actually see in practice to be an issue, and several papers have been trying to go around that. But from the point of view of speech generation, I want to mention that it wouldn't make sense for humans to learn to generate speech using maximum likelihood and teacher forcing, because unlike the machines that we're training, which are directly generating acoustic, given acoustic that is known, humans are not generating acoustic. They're generating muscle movements. And nobody tells us what the correct muscle movement should have been, right? So we don't directly generate sounds. We generate muscle movements, and we don't have those targets. So it's impossible for humans to learn to generate speech by maximum likelihood. So something else must be happening, right? And as I'll argue at the end, something like GANs, the generative adversarial networks, might be an interesting candidate for something more biologically plausible for learning to generate things like speech. So quickly, these recurrent nets can be generalized, and you've heard about it yesterday too, to 2D data, and you can generate pretty impressive images using these kinds of generalizations. Another thing I want to mention, because it has nice connections to cognition, is the introduction of attention as a central tool for many architectures in modern deep learning over the last 2 years. So we discovered the power of attention, and especially a variant that we call soft attention, content-based soft attention. This is a technical detail I won't go into, as a tool that really provided a breakthrough in our ability to do machine translation about 2 years ago. But this tool has been used in other settings in deep learning, for example, extending neural nets with additional memory. So you've already learned about LSTMs, but there's another more modern series of approaches to extending memory of neural nets with things like neural training machines and memory nets, but more generally we call these memory extended networks. And they all rely on attention mechanism, where the attention is used to focus on particular elements of the memory that are used for the next computational step. In the case of translation, and as we'll use it in speech generation, the attention is used to focus on a particular part of the input sequence. So here would be, say, an input sequence of phonemes or characters, to decide on what kind of acoustic we're going to be generating. In the case of translation, it's focusing on some parts of the input, say French, when you want to generate some output English. Okay, and we've used this for speech recognition as well. There are too many numbers here, but the bottom line of this slide is, in the last few months, Google has publicized a recent system that's based on neural machine translation with attention, using the ideas, some of the ideas, and other ideas that have been worked on by us and others for machine translation with neural nets and attention. And the difference between their work and our work is mostly scale. They've trained these systems at the Google scale on probably more data than any human can see in their life by a large margin, maybe 1,000 times what you could see in your lifetime if you spent your time reading French and English, or whatever, English and Portuguese, or any of these pairs of languages. And of course, computational power that is pretty amazing. And the result is that they're closing the gap between traditional phrase-based machine translation and human translation, at least at the sentence level, which is an easier task. I won't explain the numbers, but basically we're getting very close, at least numerically, and in terms of human evaluation, to machine translation using these systems. Okay, so now the main things I want to tell you about is audio synthesis and speech generation, focusing on an approach where we're going to try to get rid of the many building blocks that are present in speech synthesis, but also do it in a way that's not specific to speech, that's going to be completely general. In particular, one of our objectives was that we could use these things in the unconditional context. So when you're not given a control input sequence like phonemes, but let's say you want to generate music, or we had a collaboration with people at Ubisoft where we wanted to generate special effect sounds. So we train on a particular category of sounds, and we'd like to generate things like that. And you don't have the fine kind of control that you have with speech synthesis. So the next talk you'll hear about WaveNet. So this is something that was going on in parallel to our work at DeepMind and produced pretty impressive results. So I'll tell you about the thing we were working on. First paper on this is called Sample RNN. And it uses a hierarchical architecture for recurrent nets, which we think is very important in this setting, because speech has a wide range of timescales. So you have the timescale of, especially the way we were doing it with acoustic samples as the ultimate thing that are generated. So 16,000 things per second on one hand, and say a couple of words per second on the other hand, right? So it's thousands of, the dynamic range is more than 1,000. So this is a large group of students. Actually, two of them I missed the picture, but as well as my colleague Aaron Corville, and the lead student on this is Soroush Mary. And the basic architecture we're looking at has this kind of hierarchical structure, where at the lowest level we have just mostly for efficiency reasons, not a recurrent net, but a feed-forward shallow MLP, which is going to be conditioned on both the recent window of acoustic samples and on the state of higher-level recurrent nets, and which is going to generate the next acoustic sample, so a real value. But we're going to discretize that real value. We found that we got much better results if we didn't assume that the next real value was Gaussian, or even a mixture of Gaussian with a few components, but instead just made it non-parametric with, say, 256 levels or something like that. And higher up in the hierarchy, you have different recurrent nets operating at different timescales. And in this work, the timescales are fixed. So we just decide how many, after how many low-level samples each level in the hierarchy gets updated. And at each level, the states of the recurrent nets are conditioned on the state at the upper level that has already been computed. So you get a kind of unfolded graph which looks like this, and you could have more levels than this. And you generate things that, at least in terms of envelope, look right. On top, you see the kind of training data. So Blizzard is speech. Onomatopoeia are these special vocal effects, like ha, hoo, things like that. And this is supposed to be music. And these are from two of the models with different depths of the hierarchy. You can zoom in and you can see that it seems to be capturing, at least visually, what you would expect. It's hard to distinguish visually by looking at the signal. As you'll hear, we can still, of course, distinguish that it's not the real data. You can also do quantitative tests of the log likelihood. Because these recurrent nets have this nice property that's quite easy to compute, the log likelihood. Other models, like the GANs I mentioned earlier, it's not so easy, unfortunately. But here we can quantify and we can compare very precisely different models. And what we find on the various data sets is that these hierarchical architectures do improve sometimes significantly on the, in fact, very significantly on the straight RNN. By the way, what I mean by straight RNN here is without the hierarchy. These are not vanilla RNNs. These are GRU RNNs. We tried LSTM. It's about the same thing, and GRUs are a little bit more efficient, but they essentially behave the same as LSTMs.
Joshua,
yes?
I don't understand what is the goal of this. For example, in speech compression, in speech communication systems, you have an input.
Yes.
You want to compress it and generate again that input with the best quality you can. Is that what is the goal here?
No, the goal is I build a machine that can talk to me, generate natural language, and generate the sounds that go for it. Nothing, or whatever you want to control it. If I want to build a machine that's just going to spontaneously talk to me in Spanish, I could do that with these models, right?
Spontaneous, because text-to-speech, for example.
Yeah, so that be used for text-to-speech. So that's when you condition. We could play all kinds of games. I'll mention conditioning on the speaker characteristics. So now you can change the voice. You could change other factors if you have labels for them. But you could also have pure unconditional generation. So all of these things are possible.
Okay, thank you.
Yep. Also, we re-implemented the WaveNet architecture, probably with not enough computational resources. So it's hard to say if our implementation is as good as the one you'll hear about in the next talk. But in our experiments, it didn't work as well as the recurrent net, but it has a lot of the same ideas of having a hierarchy of timescales. That this one uses recurrent nets instead of more convolutional architectures. Yeah, let me skip some of these details. And we don't see the sound things here. What's going on? First time I try a PowerPoint thing on this new Mac, and of course it doesn't work. So this is unconditional generation of music. It was trained on piano sounds. This is not MIDI, this is acoustic. And this is speech. Again, this is completely unconditional. Wow.
Alright. Det förut smula and on her maps and the sea salmon. Let's end up.
Another one. So
Thing into nice. And then just speaking so all over rift.
So what all of these things sound like is someone speaking in a foreign language that you've never heard of. They have kind of the right texture, but nothing of the long-term structure you would expect so that you would hear words. And I'll come back to this later.
I mean, they have no accent. They sound English, right? But they don't sound quite like phonemes, and they're kind of they're perfect for a lot of experiments.
I'll maybe hear some more later, but yes. We asked people to compare. So these kinds of speech, unconditionally generated speech. And so we made pairwise comparisons between different 3-tier is the one that has 3 levels, 2-tier is 2 levels. The WaveNet is our implementation of the WaveNet architecture. And RNN is the single level ordinary GRU RNN. So you basically see either the 3-tier or 2-tier model working better, depending. I guess 3-tier here is working always better. And this is for music, where you see similar results. A little bit of the details. We trained on a few hours of data. Training time took from 1 to 3 days or a week. And generation time is very slow because we're generating sequentially each acoustic sample. Oops, yeah, sorry. And so I guess this is one of the reasons why why in the next set of experiments we moved on to generating one frame with a vocoder. So yes.
Texture synthesis on the full thing.
Yeah.
Where you have some signal and you take little pieces of it and you stitch it together so that they kind of agrees at the boundary. And I'm wondering if there's maybe that's.
This is very different in nature because, as you'll see, you are able to generate variations in style and prosody and speaker voice that would be much harder to do with concatenative approaches.
I see. So that would be the main metric by which you would
I don't know what is the right metric, but this is a very good question.
Often a question that is unclear to me also about GANs, like to what extent they're actually storing like lots of.
Oh, they're not. They're not. The proof that they're not storing things is that you can interpolate between, say, images or people's recordings, and you get something meaningful. I'll come back to that. So now I'm going to move on to the conditional case, but keep in mind that in principle, those recurrent nets should be able to capture the full joint distribution, including at the linguistic level, and they're not. So we're going to be cheating and telling them about the existence of phonemes and ask them to generate conditionally on phonemes. So that's another recent paper, I guess, to appear. And this is led by another student, Jose Sotelo. So we're going to be conditioning on phonemes, but we can also condition on other things like speaker embeddings. And if you had other things like style information that you had in data, you could learn to use that kind of information. Because we're going to condition on phonemes, we used not Blizzard this time, but data sets where you have multiple speakers like VCTK. And we use the attention model that I mentioned before. So the advantage of this is that we can put in the phoneme sequence without having to specify the segmentation. And the model is going to, you see this alignment thing here, basically discovers for, say, when it's generating the first frame here, it's paying attention to something, a little bit of the H here and a little bit of the I. And then, say, when it's producing the K here, well, it's influencing those frames, right? So you see that it fills that matrix to figure out which part of the input sequence it wants to look at for each frame that it generates. So that's what the soft attention gives you. And of course, what it does also is that you don't need any more. We can actually do this on characters also. And so the system will figure out the mapping from characters to whatever features are necessary to generate the sounds without requiring handcrafted linguistic transformations, which are problematic when you want to move to another language. That's not an output.
Is it generated all at once, or is it working sequentially?
Okay, so we're using, in this implementation, we're using a bidirectional recurrent net, which reads the whole sequence of characters or phonemes, generates a sequence of features that exactly the same length of that phoneme sequence. Then we use a recurrent net that goes sequentially and generates all the frames.
Maybe you can explain how the attention works. It seems like if you're working on the first few frames, you don't need an attentional unit because those other frames don't exist yet.
You're right. But it could be that when I'm going to pronounce that letter, I need to know about the future letters. So this is what this is used for.
So the attention is on time in the input, not time on the output.
The attention on the time of the input, yes. Yes, yes. We sequentially generate on the output. For each point in the output, we are allowed to look anywhere in the input.
Right, that makes sense. That's quite plausible.
Of course, if you wanted this to be efficient, you could have a little moving window because typically, the only attention is going to be on this sort of band, right? So you don't actually, if the last attention point was here, you know that there's no here. So you could have a look ahead and not have to look at everything in the front.
Where did the durations on the output come from?
I don't understand your question.
I mean, you have this sequence of states that's as many as you have letters, but the output, different states will have different durations.
It chooses whatever it needs, right? So it's a recurrent net. So it's going to generate one frame at a time, and for each frame, it decides where to look at in the input, and there's going to be also the possibility of saying stop. So it can decide that's the end.
So and that's in the lowest RNN level, or?
That's the lowest, if you want, from the point of view of generating, yes, closer to the signal. So there's an RNN which can decide, I'm done.
For this work as well, you generated the sample level, or you generate some feature vector to
For this work, we generated the level. But just because of efficiency, because we do lose some of the accuracy of the sound when we map to the vocoder representation, but it's much faster because we can generate, say, 500 samples at a time instead of one at a time. So it's 500 times faster, basically.
features sampled from a Gaussian, picture of Gaussian, or just like
Which
sampled,
features?
the one that the vocoder features, the one that you generate.
Oh, these are Gaussians, yeah.
This is a kind of text-to-speech system.
It is.
Okay.
Yeah.
So now, how you compare the quality you get with the AT&T system? They use huge amount of waveforms, and they do a search on waveform pieces.
I guess eventually you're going to have to ask people to form judgments.
I don't talk about it in the next.
So let me. Unfortunately, it seems to be a real bug that clips are not shown on that. So I'm just gonna.
For all his successes, he
This
is
is from-
accustomed to waiting for fulfillment.
This was from the data set itself, just so that you hear that the vocoder is making you lose some precision. So let me play another one.
That was a hard game to play in. Very tough.
Now, what was generated using the same phonemes?
That was a hard game to play in. Very tough.
Or this one.
People look, but no one ever finds it.
So let me play some more things now so that you see that we can play games because we're also conditioning on the speaker, so we can change the speaker embedding. So we have you can think of it like when we train, we tell it what the speaker is, and the first thing that is learned about a speaker is a embedding. That's the characteristics of that speaker. We can change that. And
for all his successes, he is accustomed to waiting for fulfillment.
Now, if we pick another speaker.
For all his successes, he is accustomed to waiting for fulfillment.
For all his successes, he is accustomed to waiting for fulfillment.
Right. We can also play games like we take two actual speakers and we can interpolate in the space of speaker representations. So here's one sentence by one speaker.
People look, but no one ever finds.
Then the same sentence by another speaker.
People look, but no one finds it.
Now we can generate things in between by just interpolating in the latent space.
People look, but no one ever finds it. People look, but no one ever finds it.
People look, but no one ever finds it.
We can also do this in other ways. And this one is directly from the characters. So
Los aumentos en el costo de la energía afectarán a tu bolsillo.
Realización de programas de radio y televisión.
Los objetos del proceso pueden estar afectados o no por él mismo.
So the way we we are handling latent variables. In this case, is we're using a variational autoencoder approach, which I'm not going to have time to explain. But one thing that it allows us to do is, in addition to the kinds of conditioning variables that are known, like speaker, we can also let it discover additional latent variables. And so now we can play with those latent variables, which presumably represent aspects of the signal that are not given in the labels. So for example, here's the original, say, ground.
And distinguish will understand your motive.
Now we can take the value of the latent variable that it figured out corresponding to this and change it.
All who can distinguish will understand your motive.
So this basically takes the same upper level representation and just changes this latent variable.
All who can distinguish will understand your motive. All who can distinguish will understand your motive. All who can distinguish will understand your motive.
Yes.
The training loss that you were using, and how did you
This
deal
is just
with
maximum likelihood.
maximum likelihood, and how did you deal with the
I mean, in the VAE, it's a proxy for maximum likelihood. But,
how did you deal with the problem of teacher forcing that you mentioned?
not in this work. I'll tell you about the GANs. So this is the problem actually, and we fixed it using a hack by injecting noise in a particular way, which is not the same as what they use in scheduled sampling, but it's kind of related. But I won't have time to talk about it. I'm already over time by a lot. So let me just say a few things quickly. So I think that the approaches that we currently have, even the GAN that I'll tell you later, are failing to discover a lot of the higher level semantic abstractions that are there. So the fact that when we condition on the phonemes, we're getting so much better generation than when we don't, it's a very strong cue that it's not able to discover or to separate the learning between these higher level things like phonemes and the phonemes. Because in principle, you could generate the acoustics by just decomposing into generating phonemes and then generating acoustics given phonemes. It could learn that, but it doesn't. If we tell it that phonemes exist, and then it does a good job. But it should be able to discover them. Phonemes are statistically salient, or something equivalent to phonemes are statistically salient. So something is wrong in the way we're training. It may be connected also to the multiple timescale issue. If you look at the log likelihood, it's paying for every bit of mistake that you're making at the lowest level, right? So in the case of acoustic, you have tens of thousands of bits that you pay for the acoustic details compared to a few bits for the phonetic or linguistic level, right? So that higher level stuff is drawn in the total cost of getting all the details right. That's potentially one of the explanations. We're exploring GANs, which are a kind of radical departure from maximum likelihood, in which you have both a generative model that you train. So that's just, think of it like a neural net that takes noise as input and generates images or sounds. And we also train another kind of network, which we call a discriminator, which tries to figure out whether the thing it sees, or hears, is coming from the training data or is coming from the generator. And I think this is much more plausible for how humans could learn, because we hear our voice, we hear other people speaking, and we hear all kinds of noises. Our brain can learn to distinguish the things we're generating from, say, the things that our parents are generating. And then using that discrimination to guide the learning of the generator to make it mimic in distribution what our training data, like our parents, are. So this is how GAN-generated images looked a couple of years ago. This is how they looked last year, and this is how they look now. So we've made a lot of progress. I want to mention quickly the thing about interpolating, why it's telling us that when interpolation between samples work, that the system is working. So if you look on the top here, the data lives on a highly curved manifold, say like this, in the input space, in the data space. So if you take two examples, unless they're very close to each other, and you interpolate, the thing in between is not going to like a real data or a real image. And what these methods are trying to do basically is to unfold those manifolds, go in a new space to represent the same information, but where everything is flat, so that when you consider the interpolation between two things, it actually is going to be meaningful. It's going to look like real data. So this is a real image. This is a real image, and these are interpolated images, and they all look reasonable. And then you can play all kinds of games like adding and subtracting, and it's kind of fun. Huh?
It still happens that it works. But is there anything in the model that tells it the space is, by interpolating, it should still make sense?
Yes. If you think about the training objectives, all of these sort of autoencoder related things, or even the GAN objective, it really wants to flatten the distribution at the top level. Like it wants the distribution to be a Gaussian. So that's like the space in a uniform way where everything is filled. Whereas in the data space, the data is occupying a thin region, in fact, and that region is going to be highly curved, which makes things hard. Okay, I think I should really stop here and give you time for questions.